Hello, my name is Ulrik Stridsman. Besides from working with high availability, I also do a lot of work around commit queues, actually helping users of NSO how to use commit queues. Let me see. I can't see it there. Let's look up here. I assume all of you have read the documentation, so you already know how commit queues are working. So I have a challenge for you today. So if I succeed, you will not have any questions afterwards. So let's challenge me about that. What we like about I can look here now. What we like about NSO is that we have these atomic synchronous transactions. So you push in your service intent, and if everything succeeds, everything will be pushed into the network. But if something fails, everything will be rolled back and no harm is done. So, and that's what we like. But I would say the problem with that is that the transaction will never be faster than the sum of all the tasks that cannot be parallelized. In this case, we will probably have one transaction in NSO and one towards the device. So if you have a slow device, it can take tens of seconds. You will never have a throughput that is faster than that time. And this is actually the reason why we added commit queues. So actually moving away from these synchronous transactions, we added this asynchronous way to you push in your intent into NSO, and then as NSO creates the device configuration and puts them on the commit queues, and then that will be processed in the rate of the in the rate that the devices can handle the configuration. And I think the main reason for start using commit queues is actually handling slow devices, because you want higher transactional throughput. And now, if you listen to the presentation yesterday that Try and Christian had about our work on increasing the concurrency in NSO to increase the transactional throughput, commit queues has become more important. So my goal today is to actually, beside from what you already know from the documentation, add some, I would say, behavioral aspects of using commit queues, and mostly how you can set some of the configurations in NSO around commit queues. I will probably touch in some use cases and best practices, but that is not the main target. Best practices. We have a lot of configuration options, so you probably have had a lot of questions. How do you combine all these in the best way for your use case? And if everything goes, it's okay. It doesn't actually matter how you set them, because everything will succeed. I think the crucial thing is to know how to set them when there are problems in the network. If a device rejects config, there is a network problem. A device is not accessible. So how do you do? And if something goes wrong, how do you handle that? There are several ways to do it. So you can do a sync from and sync to, and so you also need to look into the specific use case, what to do. And then also with this increased concurrence, LSA is also this option to scale it even further. But I will not cover anything with LSA, so I hope you don't have any questions about that. Okay, let's look at what you can actually set. We have, I would say, 3 levels where you can set configuration. I only show 2 here. One is you can actually, on the global level, you can actually set, I would say the most common you use is atomic, and you use error option. I think they are the ones that affects the behavior most, but also retry timeout can be important. And then we also have this enabled by default. It doesn't actually change the behavior, but makes it simpler when you do the commit. You don't have to push in any commit queue flags. And these are actually the levels where you can actually set configuration when it comes to commit queues. You have when you're actually on the global level. If that's not enough, you can actually do some override on the device, and then you can also directly with the commit action, you can specify parameters as well. Yeah, these are the commit parameters you can actually specify on the commit action. You can actually select if it should be synchronous or asynchronous. I will come back to some small details about that. But then we have atomic. I will come back into details about that as well, and error option. And then we have two options. One is commit queue tag and one is trace ID. And I would say that commit queue tag was, the intention of commit queue tag initially was to get some kind of tracing in logs and notifications to actually track a commit with the upcoming event. But with the introduction of LSA, tag is not the way to go. So today we recommend actually to use trace ID to get this possibility to trace transaction in an LSA system. But you should, even if you just run a single node, it is the way to go. And trace ID was introduced in NSO 5.5. Yeah, and when you do a commit queue sync, it is a way to actually act like just a normal atomic synchronous transaction. So, but it is quite similar to doing. I will get back to that one. It just doing commit queue async, but then you can actually take the commit queue ID and you can actually wait until completed. And the reason why I actually recommend this is because if you do a commit and just wait for sync and for example the terminal session is broken, you will not see any commit queue ID. So I would recommend doing that, and I would say the normal way for users of commit queues is to actually use the async and then use trace ID and or the commit queue ID to actually monitor further transaction. And I say that is important when you use reactive fastmap and nano services. And that's what I would say is the main topic that I will get back later on. There's one specific, I would say, use case of best practice is that I think the default value for retry attempt is unlimited. That means if you create a transaction that will create the commit queue item, NSO will try to actually push that configuration to the device, but it will be rejected. And as long as it's rejected, it will continue forever. And I would say the single use case where this is can be useful is if you have a lot of, for example, CE devices, and the final goal is to update them all. In this case, it can be a good thing to set retry attempts and retry timeout to quite high values to finally reach this goal. And also a comment is this: when you use commit queues, there's no actual distinction for NSO to actually. It doesn't distinct a device that rejects a configuration, or if it's not responding, it will behave the same. Let's continue. I would actually not would like to talk about this, but because I will try anyway. Check integrity is when you push configuration, for example, towards the same device, and you have overlapping configuration, it can be, for example, configuration that touches the same interface on the device. Then you can actually set check integrity to false, so you will actually allow that anyway. But now we have deprecated this, so I think it was NSO 5.7. So I will try to explain the reason why, and the reason why is commit queues, and the reason why we in NSO we fixed some old behavior around rollback and reactive fastmem and nano services. So if you have a first commit that pushes that intends to push configuration towards a device, you have a second commit that also trying to push configuration to the same device. So you will have two commit queue items with configuration to the same device that is overlapping. If the first one fails, the second commit is committed into CDB. So in this case, there is no possibility to do a rollback, because since this is overlapping configuration, the rollback will fail, and that is not the ideal way. And with the use of what we see with the increased use of commit queues with rollback, we decided to actually deprecate this. Now we come to the interesting part. See if we have. This is some invention that I try to actually explain behavior of commit queues. So I decided yesterday to actually call this service intent asynchronous state diagrams. So I'm not sure if it's a combination of some kind of flow diagram and state diagram, but up there I have some kind of scenarios that I have created. Oops. That was not the intention. Sorry. Push the right button. Up there I have created some scenarios that is actually a combination of these commit queue flags. So I have atomic, I have rollback on error in the number of combinations, and you see a number there. That is the number is also important to the last slide as well. And I also have a reserved one to make this important. But let's start with you can look at scenario number 1, and the number is actually a combination with or is this result. So when you push intent into NSO, when you use commit queues, you will probably end up in one of 3 states down here. We have this fourth also that is actually related to when you use stop on error. And as I said before, how this behaves is, I would say, is important when you actually have problems in your network. So the scope of this is actually have the service is touching 2 devices and one is not responding. So that will cause an error, and depending on the commit queue flags, NSO will behave accordingly. And just as I have some retry time set to 2 and retry time out to 5 to actually, so we get some context on the time scale. So actually, what do all these lines mean? We push in our content, it will end up in CDB. We will have a commit queue item that is in state executing, but then we have 1, 2, 3, 4 lines. What do they mean? They are actually the result of the result of what you set error option to. On the left, we have rollback on error. In the middle, we have stop on error to this intermediate state. We have continue on error, end up there. And then we have asterisk on error. What does that mean? there's actually, it doesn't actually show, there's some background picture that is missing here, but what that actually means, that asterisk error, is that when you set atomic to true, you will actually end up in some of these three states. As soon as you set atomic to false, you will always end up in this state when there is an error condition. That means if you have continuing error, you will at least have, when you set atomic false, independent on what you set error option to, you will always end up with at least one device that is out of sync. So that means you will need to do some repair action like sync from or sync to. The colors are quite bad here, and here we have actually the difference also. I'm not sure if you can see, there is a yellow line around this. So when you use when you have rollback on error, you will always end up, the transaction will roll back and all devices will be in sync. So that means if the transaction fails, you will get back to some start condition and you can actually continue from there. But if you don't have rollback on error, you will always end up with at least one device that is out of sync. But you also have this intermediate state that is stop on error. And I'm not sure if anyone is using stop on error. But when you end up in stop on error, you have the choice to either do a rollback or you can just unlock, delete it, and end up in this state where all the devices are out of sync because no configuration will be pushed to a device. Now I'm going to make a distinction between what I call simple services. And simple services are services that do not use reactive fast map or is a nano service. And in this case, you have everything is, I would say, working just as expected. Depending on how you set the flags, you will either end up in this state, or this state. Now we'll get back. Now, as soon as you historically started using reactive fastmap or nano services, and this is important, up to NSO 5.6, we had that rollback on error was not working. It was, I would say, useless. And my conclusion here is that I think commit queues were introduced in NSO. I think it was NSO 2.x or 1.x. I'm not sure, but it was actually the time before we started introducing reactive fastmap and nano services. So it was actually a choice by design at that time. But now when our users are starting using reactive fastmap and nano service to get this asynchronous behavior and making more complex service integrations, this has become really important because ending up in a state where you have devices out of sync just causes a lot of extra work. And so what we did is, and this is, I think, is part of the work we have done with increasing concurrency. We actually, in NSO 5.7, we got back on track, and now you can actually use rollback on error when you have a nano service or a reactive fastmap service. I'm not sure if I can actually, we can actually visualize this, but when you use rollback on error, and if you have, for example, a nano service, it is only the last transaction that will roll back. So if you have a multi-step service, it will only the failed part that will be rolled back. So you will still have some service intent and possibly some device configuration already in CDB. And let's get back to, I will just mention the NSO Scenario Explorer. And during my work with commit queues, I actually came up with some scenarios, so that's why we have these numbers. And if you're interested in investigating and learning and discover the behavior of NSO when it comes to commit queues, I will recommend to actually have a look at the NSO Scenario Explorer. We have this available in a open Git repository, so it's free to download. And I will have this workshop later today, actually going through how this can be used when you develop services to actually in depth actually discover the behavior of NSO in a step-by-step manner. And that was what I had today about commit queue. So I hope you have no questions for me. I challenge you.
So yeah, challenge Ulrik now with questions. So raise your arms. No, looks like you explained it well.
Thank you.